There are several different kinds of electrical components, but one of the ones that shows up almost every single time we build a circuit is a wire. So it makes sense then to talk about what exactly it is that wires do. So if I sketch what a wire looks like, it is basically just a cylindrical piece of metal, like so. And because it's made of metal, it is a conductor. All right, and so we had some rules that we developed for conductors. And the most important one for the purpose of electric circuits is that the potential on a wire is constant. Okay, so I don't know what it is, but whatever it is, it's the same everywhere along the wire. So maybe it's like 13 volts at every different place. So 13 volts here, 13 volts here, 13 volts here. Okay, that's the rule for conductors. Now, the way that we typically sketch out diagrams of circuits is with this simplified set of symbols. And so the symbol for a wire is probably exactly what you would expect. It's just a line. If you see a line in a circuit diagram, you can assume that it is a wire. Even if it's not strictly a wire, even if it was some other kind of conductor that was part of a circuit for some reason, like maybe you used a paper clip as part of it, so you could have a paper clip like this, and then you just kind of kept going with the circuit, we would still draw that as just a wire, so just one long line. We wouldn't typically sketch in the other component. Or if we had, like, say, a metal washer, like this, again, we would just draw that all as one wire. If you wanted to have multiple wires that were connected to each other, then we typically do that just by drawing a wire that branches off of another wire, like this. And so sometimes you'll put a dot there just to emphasize that they're connected, but with or without the dot, that typically just means that we have multiple wires that are all connected together. And keeping in mind this rule that conductors have a constant potential, everywhere along that wire, the potential will be the same. So including the paper clip, including those other wires that branch off, because it's all one conductor, it's all the same potential. Okay. So the other really important electrical component that's going to show up in pretty much all of our circuits is a battery. So what do batteries do? Well, if you look at a battery, and I would encourage you to find one in your house, just some AA battery, AAA, D cell, any battery that you can find. If you look at it and read all the fine print, somewhere on it, it will say something like 1.5 volts. And that's a hint about what the battery does, because it turns out that batteries produce some constant potential difference across their length. Okay, so if you measure the delta V from one side to the other, which you might draw like this. Remember, we can do that with a voltmeter. What you would find is that there's a 1.5 volt potential difference. Okay, so the thing that batteries do is they raise the potential by some amount. Okay, so batteries have a constant delta V between the ends. Okay, there's a special name for that. We use a squiggly E like this, so it's basically just a cursive E. And that is the same thing as the potential difference for the battery. Okay, I'm not going to tell you what the E stands for, but if you have to read it out, then we call it the EMF. Okay, so the EMF was once an acronym, but it is no longer. Now EMF is a term in and of itself, and if you want to know what that stands for, you can look it up, but I would discourage you from doing so because it's outdated terminology. Okay, you might wonder why we have a name for the EMF if we could just use delta V. So for an ideal battery, those are the same, but for a real battery, there's a slight distinction, which we'll learn about later on. But you can think of the EMF as just being the potential difference across the battery. Okay, So there's a symbol for a battery that we use in electrical circuits. Okay, so the symbol is like this. We have two parallel lines where we have a wire coming in and then another wire coming out, and one of the two parallel lines is longer than the other. Okay, so this is the symbol for a battery that I use most often. Sometimes to remind people which side is the positive side, you can put a plus by the longer wire. You can always assume that the longer wire is positive, whether there's a plus or not. The plus is mostly just as a reminder. Sometimes people will put two pairs of vertical lines. So if I do, for instance, like this, okay, that's another way to draw a battery. The difference is really just personal preference. There's not really a difference in meaning. And again, sometimes people will put a plus here to indicate that the longer line is the positive side. Okay, so as I told you, the thing that a battery does is it raises the potential by some amount. So let me sketch out a circuit like this. So let's say that we have two batteries that are in series. Okay, here's two batteries in series. And what I know is that the potential difference here is 1.5 volts. And the potential difference here is 1.5 volts as well, if these are normal, let's say, AA batteries. So I know that between the wires on either side, that will be the difference. Okay, so maybe over here, this is like 7 volts, just any number. I don't know what it is. I just pick one. And then over here, it's 8.5 because I've gone across a battery towards the higher end, so towards the longer wire. So that means that I have 8.5 volts here. And then if I cross another battery, then it is 10 volts here. Okay, so you might wonder why I started at 7. I just picked a random number. Typically, what we will do is pick a spot to call 0, and then work from there. It's okay to have the potential be negative in some spots. Nothing bad happens. We just kind of pick a spot and start. Okay, if we have a more complicated network of batteries, let's say we have a battery like this, and then maybe another one like this, and we could have a branch here, like that, and then maybe on this side we have a battery that's backwards, and then maybe another one that is like this. Okay, well, so like I said, we typically want to pick a spot to call 0, so I'm just going to pick a spot over here and call that 0. Then that means that this wire is going to be at 1.5 volts because I have gone up a battery, and by up I mean from the smaller side to the longer side, so from the negative to the positive. If I go across this next battery, then I can see that this wire is at 3.0 volts because I've gone from 1.5 up 1. Okay, so you can think of each battery as a set of stairs, right? If you go one direction across the battery, you're going up by 1 EMF. If you're going the other way, you're going down. Okay, so everywhere in this little T-shaped piece here is going to be the same potential, so all of that is at 3 volts. If I then go up to the top, I'm going up another battery, so that will bring me up to 4.5 volts over here. All right, meanwhile, if I go from the 3.0 volts to the right, then I'm going down a battery. So notice I'm going from the longer wire to the shorter wire, so from the positive side to the negative side. So that will make this wire be 1.5 volts. And then when I go down this other battery, well, I'm going from the shorter wire to the longer wire, which means that this will be 3.0 volts. Okay, so don't read too much into the fact that batteries have a positive side and a negative side. That doesn't actually tell you one's positive and one's negative. You know, for instance, if I circle one of these batteries, that battery has both sides at a positive potential the way that I've drawn it. If I picked a different place to call 0, then they could both be at a negative potential. All that the plus and minus tells you is that one side is at a higher potential than the other.